Hi everyone. In the last two lectures, we've been studying the crystallographic structure of metals and alloys. And at this point, we should remember that most of the metals and alloys are crystalline. We should also remember that the most common crystal structure in metals and alloys are three structures, which are face-centered cubic, body-centered cubic, and hexagonal closed packet. In this lecture, we are going to dig deeper and go further in the crystallographic structure of metallic material. First, we need to know how the atoms arrange themselves in a crystalline structure or in crystalline metals and alloys. In one dimension, there is only one possible way to stack the atoms or to pack the atoms or for the atoms to be arranged. It is something like this. There is no other possible way to arrange the atoms in one direction. In two dimensions, however, we've got two possible ways to arrange the atoms. The first one is shown here, which is the second row of the atoms goes on the top of the first row. And the third one does the same. The fourth one does the same, and go on. For this structure, for this packing, if we take any atom, we will find that this atom is surrounded by four neighboring atoms. Connecting the center of these neighboring atoms gives us a square shape. This stacking is called squared closed packet. On the other hand, which is more energetically favored, the second row of the atoms goes in the depression of the first row, and the third one goes in the depression of the second row, and go on. For this stacking, for this packing, for this arrangement, each single atom is surrounded by six neighboring atoms. And again, connecting the center of these neighboring atoms gives us a hexagonal shape. This kind of arrangement called hexagonal closed packet. Packing in three dimensions. For the first scenario, square closed packet, and taking the same way of packing, the second layer of atoms will go on the top of the first layer, and the third one will go on the top of the second layer, and go on. The arrangement or the alignment of the first layer is exactly the same as the arrangement of or the alignment of the second layer and third layer, and so on. In the hexagonal closed packet arrangement, the second layer of atoms goes in the depression of the first layer. The second layer will go on these depression, or these depression. It doesn't matter. It's the same, exactly the same. And this gives the alignment of the second layer is different from the alignment of the first layer of atoms. The position of the atoms in the first layer is different from the position of the atoms in the second layer. And then this to say that the alignment of the first layer is different from the alignment of the second layer. If we need to place a third layer on the second layer, we have two possible ways. The first one is placing the third layer on the depression of the second layer on these depressions. these depressions, to cover these voids. These voids are called tetragonal voids because they, the shape of them is tetragonal. It is out of scope of this study. Anyway, placing the third layer on the depression on the second layer of the second layer on these depressions, note these depressions, will give us arrangement for the third layer exactly the same as the arrangement of the first layer. Here, in a 3-dimension, the position of atoms of the first and third layer are exactly the same. Thus, it is to say that the alignment of the first and third layer are exactly the same. Now, taking the same scenario and placing the third layer on the depression, on this depression of the third layer, the fourth layer on the third layer, we will get arrangement or stacking in this way. The arrangement of the first and the third layer, the alignment of the atoms in the first and third layer is exactly the same. The arrangement of the second and the third layer is exactly the same. Thus, the 3D arrangement or 3D stacking of the atoms for this scenario is alignment A, alignment B, alignment A, alignment B, or AB, AB. Now, taking one set of atoms and hidden the rest of the atoms, we can see that this alignment is just for hexagonal closed packet. This is A, this is B, and this is A alignment. Now, the other possible way to place the third layer on the second layer of the hexagonal closed packet is placing the third layer on these depressions to cover these voids. The third layer goes on these depressions and they cover these voids which are created by the first and second layer. As you can see, the third layer alignment is different from the first layer alignment and the second layer alignment. Those we call this alignment A, B, C, and then repeating the same scenario A, B, C. Those the alignment of this the stacking of this alignment or the stacking of this arrangement is ABC, ABC. Now doing the same as we did before, taking one set of atoms and hidden the rest of the atoms, we will get face-centered cubic structure. The face-centered cubic structure is this structure. So those, the alignment for the face-centered cubic is ABC, ABC, which is different from hexagonal closed packet, which is AB, 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 and so on. Those again, the hexagonal closed packet in 2 dimensions can give us 2 possible arrangements. The first one is for hexagonal closed packet structure. Now I'm AB, AB, and the second one is for the face-centered cubic, which is ABC, ABC, and so on. I just want to stress that the hexagonal closed packet for the atomic packing in 2 dimensions is different from the hexagonal closed packet for the crystal structure. The hexagonal closed packet for the crystal structure, as we saw in the last slide, this is for the crystal structure. The one that we studied in the beginning of the lecture is for alignment of the atoms in 2 dimensions. So we need to recognize the second one from the first one. And we need to know, and at this point, I just want you to recognize the alignment of the face-centered cubic, which is ABC, ABC, and for the hexagonal closed packet, which is AD, AB. So far, we've been defining the crystalline structure or the crystalline material as the material with a special arrangement, special atomic arrangement. The atoms are arranged themselves in a special way, in a certain way, in 3 dimensions across the crystalline material. However, in the real world, this is not the case. The metals that we see around us has many entities, small entities inside them, in their microstructure, each of which called grain or crystal, each of which has a special arrangement of their atoms, of its atoms, special arrangement of its atoms. This called orientation, the grain orientation. Let's suppose that this FCC metal or BCC metal, each grain of these are BCC structure, but the orientation of each grain is different from the orientation of the neighboring grains, creating what is called a grain boundary. Due to the orientation differences between this grain and the other grain, there is a mismatch in the adjacent area. The adjacent area here, which is the area between this grain and this grain. The mismatch between the orientation in this grain and the orientation in this grain, creating what is called a grain boundary. Thus, the microstructure of metals and alloys consist of grains and the grain boundary. So it has grains and the grain boundary. If the metal has many grains in its microstructure, it is called polycrystalline. Poly means many. So it's polycrystalline material. All the material around us, all the metals around us are polycrystalline material. They have many crystals or many grains, and there is a boundary between these grains due to the orientation differences, the orientation mismatch. Again, grain and the grain boundary. If the material has only one grain, let's suppose that we can cut out this grain, cut it out as a separate material. So this grain has only one orientation, and it is single crystal. Thus, the material with the same orientation, no grain boundary, called single crystal material. Single crystal material. So we need to understand the differences between single crystal and polycrystalline, and we need to understand the difference between grains and the grain boundary or grain boundaries. The concept of the grains and the grain boundaries is exactly the same as the boundaries between countries. Let's presume that this grain is a country and this grain is another country. Each country has its own system, and there is a differences between the system of this grain, the system of this country, and the system of this country. In the area between them, which is the boundary between them, we can see the mismatch between the orientation of this country and the orientation of this country. For some single crystal material, some, not all, some single crystal material, the mechanical properties and physical properties depends on the direction of measuring, the direction of the direction that we take the measure on. For example, and because you are mechanical engineers, so we're gonna take modulus of elasticity as our example here to make it clearer. If this is BCC structure, this is single crystal material with BCC structure. If we measure the modulus of elasticity in this direction, which is 001 direction, this direction, 001 direction, it would be different from the other direction. Which means if we test this material, this crystal in this direction, we will get modulus of elasticity different from the modulus of elasticity if we test it in a diagonal direction. The direction starts from the upper right corner of this face to and ends at the lower left corner on the back face. This direction. The modulus of elasticity of these two directions is different. The modulus of elasticity of the other direction, for example, 101, is also different. Here, the modulus of elasticity of some material. Aluminum exhibits 63 modulus of 63 gigapascal modulus of elasticity in 100 direction. It exhibits 72 in 110 direction and 76 in 111 direction. The differences between these three directions is not that significant. Copper, which has FCC structure, aluminum has FCC structure. Copper, which has FCC structure, exhibits more significant anisotropy. This phenomenon, by the way, this phenomenon called anisotropy. Anisotropy is the phenomenon that we have different mechanical properties or physical properties, depends on the direction that the measures are taken. So copper, which FCC structure, has 66.7 gigapascal modulus of elasticity in 100 direction. The modulus of elasticity is doubled to 130 in 110 direction. It is even higher at 111 direction. The anisotropy of metals and alloys does not depend on the crystal structure. For example, iron with BCC structure exhibits 125 gigapascal in 100 direction. It exhibits different modulus of elasticity in this direction and in this direction. On the other hand, tungsten with BCC structure exhibits the same modulus of elasticity in the three tested directions. This material, any material, exhibits the same mechanical properties or physical properties in all direction called isotropic. So we've got two concepts in this slide: isotropic material and anisotropic material. Isotropic material, the material that exhibits the same mechanical and physical properties in all tested in all directions. So the direction of testing has no effect on the properties of the material. In contrast, anisotropic material has different values of the mechanical properties and physical properties, depends on the direction that these measures are taken. In our previous lectures, we defined the theoretical density, which is the number of atoms divided by the volume of the the volume of the unit cell. Now we need to define another two densities, which is linear density and planar density. Let's take FCC crystal structure as an example. If we need to measure or determine the linear density of this direction, the linear density means the density of the atoms in a direction, in a particular direction. If we need to determine the linear density of 110 direction, this direction, we need to know how many atoms in this direction, how many atoms are there in this direction. And it is obvious that we've got one atom in the middle plus half atom in on this end and another half atom on this end. Thus the number of atoms is 2. This divided by the length of the direction in terms of R. So we've got 2 R's here plus 1 R here and 1 R here. Thus the total number of R's is 4 R's. Thus the linear density, which is the number of atoms divided the number of atoms in particular in a certain direction, divided by the number of atoms, divided by the length of the direction. Number of atoms divided by the length of the direction, then the length of the vector in term of R is 2 for this direction. In FCC for 110 direction, in FCC structure is 2 divided by 4R or 1 divided by 2R. The planar direction is defined in the same way. It is the number of atoms. The number of atoms in the plane divided by the area of the plane. Number of atoms divided by the area of the plane. Those for 110 direction, 110 plane, this plane or this plane. The number of atoms is 1 in the middle plus 1/4 atom in each corner. Thus, we've got 2 atoms, 1 in the middle and 1/4 in each corner. The total number of atoms is 2. And we remember this relation between the R and A, which we can get the area of this plane as a function of R. Thus the planar direction, the planar density of 110 plane equals 2 divided by 8 square root of 2 times R square, or 1 divided by 4 times the square root of 2 times R square. We come to the end of studying the crystalline structure or the crystal structure of metals and alloys. And at this point, we should be aware of all these concepts. Unit cell, what is the meaning of unit cell? Metallic crystal structure, point coordinates, crystallographic direction, crystallographic planes, how to define planes in a crystal structure, how to define direction, how to define a point coordinates, how do we determine theoretical, linear, planar densities, what is the difference between crystal structure, single crystal and polycrystalline material, or single crystal versus polycrystalline material, anisotropy versus isotropy, and non-crystalline material or non-crystalline solids, amorphous material versus crystalline material. We need to be aware of all these concepts in the end of this lecture. Thank you very much for your listening. And if you got any questions, as before, I encourage you to put any question or any inquiry on Google Classroom. Thank you very much again.